either TE versus TM. TM is the one that does have what? Brewster's angle?
Brewster's angle.
Brewster's angle is very important. And that means at a certain angle, nothing is reflected, which is remarkable considering normal incidents it is reflected. And any questions about that? Now, I just asked you to do the problems that in Whitworth's book. They're very basic. The problem I gave before on TE was a better problem, in my opinion, had more involved with it.
And you did say, for the problems that you posted for your own, you found magnitudes of all the E and H fields.
Always the transmitted fields, E and H are magnitude in
Yeah.
the real world. Phase is nothing of importance unless you're doing communication work. Then phase or radar, if you're trying to do something with that signal analysis from a reflected wave that you sent, then phase becomes important. Primarily, though, it's magnitude. All right, well, if there are no questions, I hope everybody did that stuff. We're about to move in to the next chapter, which is waveguides. Now, this is chapter 7 of the book. Yeah, the way Dr. Whitworth's book is structured, he goes through and he gives you equations that apply to waveguides, but he doesn't actually solve Maxwell's equations and show you how they're derived or developed until later. What I'm going to do is I'm going to start with Maxwell's equations and derive these. For waveguides, this is in chapter 7. I got to say this too. Anything that has a constant cross section and contains electromagnetic energy or power for it so that it propagates. For instance, a fiber optic tube. You know what fiber optics are, everybody? Right? They're optical electron. That is a waveguide. A coax cable. I hope everybody understands what a coaxial cable is, but this may not be. This isn't exactly coaxial, but a cable with a outer woven aluminum kind of braid, and then an inner core that's copper. That is a type of waveguide. It's a transmission line. We've talked about that. Other waveguides and the waveguides we're going to be looking at in chapter 7 are made of pure metal on the outside, and they're rectangular and they're very long. But the wave bounces as it goes down. Now that's the one I'm going to talk about. These are called rectangular waveguides. We'll do fiber optic, but we start with rectangular. They're very common. How many own a microwave oven here or have access to a microwave oven? If you don't have access, you don't know what a microwave oven is? God help us if we don't. All right, well, a microwave oven has something in there called a magnetron that generates electromagnetic energy, and it uses an actual very short waveguide typically to conduct that into the cavity where that's where you put your food. That's a resonant type of thing. So, did you have a question?
Is a microwave and a microwave oven two different things?
Microwave is a frequency band. When you say microwave, typically,
Like
you mean
the thing where you put your food in? Yeah,
that's a microwave oven.
Oh, okay, yeah, I got one of those.
But when I say microwave, I mean microwave oven.
Okay.
It's a loose term for it.
Alright.
I want to say this too. When I was in the aircraft, I was doing weapons consulting in the summer of '87. I was out in the Caribbean on the Eisenhower. Everywhere they're doing any kind of power, they got radar, they got telecommunication stuff. They have more radars on there than I knew what to do with. They have target acquisition radars, they have navigational radars, they have 3D radars. They have everything and over all these frequency bands, but they use waveguides, rectangular waveguides, to conduct the power throughout the ship. So you see all these, they look like pipes that are rectangular. Now, in a waveguide, the one thing sailors aren't really good at, from what I can tell, is not damaging things in their environment. You're not supposed to hit them with a hammer or anything like that. If you put a dent in them, it causes a defect. It will cause reflections in a hot spot and causes problems. But it's used everywhere for high power microwave transmission. Microwave to me is anything over a gigahertz. Maybe a little less than a gigahertz is microwave. Gigahertz to about 100 gigahertz is the microwave range. 77 gigahertz is sort of the upper band. Some target acquisition radars get into the 80 Russian radars. But once you get above that, you're really starting to dabble into the optical. So, let me just talk to you about a waveguide. First, it's a rectangular tube like this. These are all, this is chapter 7. And these are waveguides. I usually bring down an example of waveguides. Unfortunately, I didn't this time. I will. Can you send me an email, bring waveguides down there next time, or somebody send me. Normally what they do is they'll call the horizontal dimension. I'm just going to blow this up. The cross section doesn't change. Usually this is the z direction. But if we look at this, and this is consistent with Wentworth's book, if this is x and this is y, a waveguide's a metal surface. Let me draw that a little bit. It'll have a horizontal dimension a, and it'll have a vertical dimension b. Now these guides, the thickness on these things, on the walls, is mini skin depth, so you don't worry about skin depth effect with a waveguide. And what happens in a waveguide is actually, it causes the wave, either T or TM, to bounce up and down it. So if you're looking at the side, wave is bouncing like this, which means, and if it's air-filled, the velocity in that direction of energy or of the group velocity of energy flow is always less than the speed of light. If this is the speed of light, then there's less of the, if this is moving speed of light in this direction, the component going that way is less than the speed of light. But that would be of energy, all right, the velocity of energy or group. I just want to get you an appreciation for this. How do we go about figuring out how this stuff works? Well, guess what? There are two types of modes to this. There's TE and TM modes. Shocking, I know. I want to see, I think Wentworth's book says TE first, but I want to make sure. Or does he do TM? Oh, he does TM. Okay. All right, so he does, this is on page 388. He does TM first. I prefer TE. T is the dominant mode. But this is going to be, for this propagation, I'm going to go through and just start with Maxwell's equations. My goal is I'm going to start with Maxwell's because I'm going to give you guys a tip. When you go into the real world, if it's just low-level stuff, you got an application, you got to get a piece of waveguide to hook an antenna to a power supply, you don't need to do this. But when you get into the higher level, especially with some of the newer stuff coming out where you have to design something, a waveguide. And a lot of waveguides are circular. They're not rectangular. Or several more. We don't cover circular waveguides in detail here. I'll mention how you go about it. And the reason they don't is the differential equations that govern them have Bessel function solutions that we don't usually cover. Wentworth's book doesn't cover. So when you do this, you got electromagnetic fields here. And in general, the way we do this, we're going to say, well, if you've got electromagnetic fields here, you've got to start with the electromagnetic equation. So curl of H, and we're going to assume these are lossless guides, lossless waveguides, lossless dielectrics in the gut. What it means is the material inside this waveguide, inside the waveguide, like in here, is going to be something that doesn't lose, has no loss, effective loss. Do y'all follow me? And it's important it doesn't lose any energy, or the waveguide is not a waveguide per se. It's just an area that's going to heat up. You want something that will allow energy to propagate. So you start with curl H, and generally speaking, you can assume sigma is 0. That means this is going to be just J omega epsilon times E. I hope everybody can appreciate that. Then after that, you're going to have, by the way, what law is this? What is it called? Ampere's. Very famous man.
Faraday?
Ampere's law, right? Ampere's is always the H field, or amps, right? Michael Faraday's law of induction is the E field, which is the next law. Curl of E. And this is going to be equal to minus J omega mu times H. Now I'm going right into the phasor domain. I could write it in the time domain, then I can make the necessary changes and say, now we're going to the phasor domain. But these are the two equations in the phasor domain for a lossless electromagnetic event.
Never mind.
Here's what it is. Curl of E, this is the formal way, minus d b dt. Curl of H is equal to J plus the partial of D with respect to D. These are two fundamental equations. What normally happens if you wanted to find a formal proof, you would say with the first one, Michael Faraday's, we're going to let B is mu H. Y'all remember that? B is permeability times the H field. Then anytime there's a time derivative, you bring out a J omega when you go to the frequency. Y'all remember this class? Yes? No? I'm not trying to, stun you with something. This is old hat. And by the way, when you get out of here, I mean, if you can't do what I'm about to do, really, you don't want to interview and say you had electromagnetics. This guy asks you something just to prove you can't do that. They're going to wonder, really? It's like, you give a voltage across a resistor and you can't find the current. Did you really have circuits? This is sort of the level of understanding I'm talking about here. For this one, you simply let sigma 0, so that goes away. Then D is epsilon E. Wherever there's a time derivative, you bring out a J omega. That's where those two laws came from. Everybody with me on this? Okay, now we need one equation with one unknown. I'm going to go for E here. So now I get curl of E is equal to minus J omega mu. You understand I took another curl of this one, right? Two curls here, and I got a curl of H that I use this for. So then I put J omega epsilon times E. By the way, how many have interviewed for summer jobs or anything like that? Any kind of jobs related to your background in electrical and computer engineering? Have you been given any kind of a questionnaire to see if you understand? What did you interview with? Who?
There was a company in Minnesota that designs test circuits.
Did they give you a basic circuits quiz or something?
Mm-hmm.
Now, I know something about what goes on. I don't know exactly what they do, but one of the challenges they have with all these weird online degrees, and during COVID, people could take courses online and literally come out with B's and A's and not know what they're talking about. So they always find some way, usually putting a template quiz on you. And if you can't come through that with like 99% or 100%, then you're really not of interest to them because there's too many questions they have. That's the truth. So just make sure when you take courses in engineering, physics, mathematics, realize that is how you're going to make money. It's not there just to check boxes like in high school you had to take, the history of Brazil or something. This is stuff, if you don't know it, it's going to hurt you. And that's the reason organic gardening, I don't care. This stuff you don't know, it may hurt you, really. All right, back to this thing. Y'all agree with that? Now I'm going to use the actual, they'll never ask you to solve the whole thing, I don't think, unless you're applying for graduate school. For this one, it becomes gradient of divergence of E, just as before, and it's minus del squared of E, and that's equal to minus J omega mu times J times omega epsilon E. And here we see J times J is going to be equal to minus 1 where the minus is plus. So this becomes omega squared mu epsilon times E. And then on this side, we do one thing. I don't know how many remember this, but we have to make assumptions. One of the things we do is assume it's charge-free region. And that means this is equal to 0. Does everybody understand that there's Gauss's laws, divergence of D is equal to rho V if it's charge-free, and it means in this dielectric, in the region inside this rectangular pipe, we're assuming that there is no bound charge in regions, which is a very fair assumption. So we get that, it's equal to 0 right here, and that means this goes away. That's minus del squared of E. Finally, I can get it all on one side, and I get del squared of E plus omega squared mu epsilon E equals to 0. Now, this is in the phasor domain. When you see omega standing out like that, or a J omega, you know you're in the phasor domain. You probably remember that, right? Now, here's where the assumptions come on. Well, let me just make one point. So, when there's two polarizations, TE and TM, okay? Now, if you have a TM polarization, and this is the first one he talks about, it means transverse magnetic, but I want you to understand what it means in this context. So if this is, try to do it this way. I'm taking a side shot of this. If this is the Y direction and this is the Z direction, what I'm trying to show you is this would be height B here. And if the wave is propagating in this direction, it's bouncing back and forth like so. I'm showing you the path, all right? Now listen, this is important. When they say TM polarization, it means the H field in the direction of propagation, which is Z, is 0. With me on this? So there is no H field that will have a component in the Z direction. The E field can. You all with me? It means the H field is literally out of the board, or it's in the XY plane. Can you appreciate that, class? Which the E field could have a component, and I'm trying to demonstrate this using this little diagram. So I said that the H field has to be out of the board, right? I'm showing you is this the Y direction here, but just follow me. If that's the Y direction, I said, the H field has to be perpendicular to the Z axis. This, I might use that mark. This is the Z direction here, and I'm trying to be clear about this. So if the H field is perpendicular for TM, now does everybody understand the reason they say that? By the way, this is the same thing with if it's incident at an oblique angle, but for this one, it's a little easier to see. So H field is like this, right? It means the E field could be, if I get it right, if this is black marker indicates E field, the E field could be in this direction if it was propagating straight, right? But if it's propagating like this, it hits, you see how the E field has a component in the Z direction. Do you all see that, class? So now we come over here and we say, we're going to assume TM propagation. Let me erase that. Let me go over here and do it right here. I want to get this part of the board. It's TM propagation. So there is an E field in the Z direction. Now this is the classic way to do it. And I want to say something to you. If this seems a little abstract and a little hard sometimes to really appreciate, you're not the first bunch of students that have ever thought that. I thought that when I was where you said. When I really started to appreciate that was in graduate school, when I really was living with this day in, day out doing stuff. Then you see how all this stuff makes perfect sense. So we're talking about TM polarization. That means HZ equals 0. Now I look over here to that del squared equation, and del squared of E plus omega squared mu epsilon E equals 0. I'm going to make a statement here. I'm not going to really just badger you about this. E field in general has 3 components, right? An X, Y, and a Z. This del squared operation for just the EX component will have 3 different derivative components. It'll have second derivatives with respect to X of EX, or say the X, yeah, X. Second derivatives with respect to EY, and second derivatives of EX with respect to X, second derivatives of EX with respect to Y, second derivatives of EX with respect to Z. That's just for the X component of EX. So if there's 3 components, there would be 9 differential equations that would be coupled. We're not going to do that. I mean, the only thing really smart enough to do that in an efficient manner is the actual materials themselves when exposed to the electromagnetic field. What we're going to do is look at TM polarization, and it only has an EZ component, right? The HZ is 0. That's by definition. So this, if for EZ, I have only an EZ components, that del squared becomes second derivative of EZ with respect to X squared plus second derivative of EZ with respect to Y squared plus second derivative of EZ with respect to Z squared plus omega squared mu epsilon EZ equals 0. Now, I'm only looking at the del squared operation operating on EZ, but it is unique in the fact that HC is 0. And solving that actually gives me all I need to get the other field components, believe it or not. You're about to see it. Ready? So whenever I see something like this, I do two things. I wince thinking about the amount of math I'm going to have to face solving. And then I think I'm going to make constants, create constants, make life easy. First constant is this one. And I'm going to say, now Wentworth's book calls it beta, or just beta, I think, unguided here. And he's going to say that's equal to omega square root of mu epsilon. Now the reason he does that is because if you think about free space is not in a waveguide. It's just waves propagating in the atmosphere with nothing binding them. Follow me? There, if it's a lossless media, beta has to equal to omega times square root of mu epsilon. Do you remember this, guys? So that's why Wentworth's book, if you've got a book, you can look at this. He'll use beta unguided. That takes care of this right here. Then, then I'm going to do something else. I wish I would have written that thing over there. I'm going to recreate that in another space. Waveguides is something I enjoy. Fiber optic waveguides, the way it's done in the book, it uses a circular guide, but it doesn't solve the differential equations, which seems a little wrong, but I'll talk about that. So I come down here, now I've got that taken care of, but we do something called separation of variables. So we're going to see if we can do this. We're assuming EZ is only going to be a mathematical function of x times some mathematical function of y times some mathematical function of z. Do you remember separation of variables from differential equations? If you can separate variables, it's a powerful tool to get a general solution, because you get solutions just to x, just to y, and just to z, and then you combine them. Do y'all remember this class? How many do? In mathematics, do you remember it or not? Did you have differential equations? Did you have it here?
I remember like if you start going over, there was just a lot of terms.
All right, maybe the terminology is something, but this is real important. Sometimes I'm challenged. Look, if you're in sales, you don't need to know this, all right?
Oh, good.
You don't need a mechanical engineer who's brilliant to sell a car to you, all right? You just don't. And same with electronics. But if you're going to do any design work, any kind of troubleshoot, anything like that, you have to understand something basic about the tools used to create the vehicle or the radar, whatever. And separation of variables is very useful on EMEG, where you have linear equations. So I take that and I stick it in here. Now take a look at this. If I take any of these derivatives, say second derivative of EZ with respect to x squared, that's two derivatives just on the x function. So what they do is usually label it as just x double prime yz. We don't bother putting the arguments y, z, and x inside there. Do y'all follow me? And if you wanted the second derivative of ez with respect to z squared, that would just be z double prime times yz, or yx, pardon. Y'all follow me? So coming over here, just watch this and it'll be clear to you. I'm going to take two derivatives with respect to x, so I get x double prime yz plus, this becomes x y double prime z plus, and this becomes x y z double prime plus, now I just put in beta unguided squared here, right? Because that's omega squared mu epsilon, which is beta unguided squared, times x, y, z equals 0. With me? And now we do the magic here. This is a neat thing. We divide everything by x, y, and z. When we do that, my back's bugging me today. When I do that, what do I get? I get x double prime over x plus y double prime over y, right? Plus, and this is z double prime over z. Remember, x, capital Y, and capital Z represent functional forms of just functions of x, y, or z. Like it could be sine of ax or cosine of by, something like that. But here, what happens? Plus just beta unguided squared equals 0. Now we have one equation, right? And we have separated out the functional form of x, y, and z into separate little additive forms, right? And here's the argument here. Remember, x is only a function of x. Just listen, I'll try to make this clear. That means this is only a function of x, right here. That means this is only a function of y. And it makes this only a function, I'll call it, h of z. Y'all with me? I want you to, this is a real important point. That means if you have just a function of x, and you're adding it to just the function of y, and you're adding it to just the function of z, and it's equal to a constant. If I took beta and got it to the other side, it would be a constant. Do you all see this? The only possibility is all these terms, this, and this, are just constants. They can't be anything else. So if you think about it, suppose this one is like sine of 2x. Even if these two are constants over here, sine 2x doesn't always equal those things except at specific points when x is certain values. But this has to be generally true. And what that means is we create new constants, and I'll do it here. So we say, because of that fact, now we're going to say that x double prime over x, we're going to call that minus beta x squared. We're going to call y double prime over y minus beta y squared. And we're going to call z double prime over z equal to minus beta z squared. You might want to make a note. In Whitmore's book, he's just going to say this is minus beta squared because he's saying beta will be assumed to be related to the direction of propagation of the wave. In fact, the wave has to go in the z direction because it's confined to do so. Okay? Now back to this. So now I'm going to put the differential equation form. So here I have the second derivative of the functional form of x with respect to x squared. Let's multiply both sides by capital X. And then shift that to the other side, plus beta x squared times x equals 0. Just take note here what I've done. Multiply top and bottom by the functional form of x. Now I have x double prime equals minus beta x squared times x. Take that to the other side, so you set it equal to 0, and this, in fact, is what you have. You all follow me? Can you follow me, John? All right, what's the solution to that? This is of the general form of what? Second derivative of y with respect to x squared plus, and you might say this could be gamma squared times y equals 0. What kind of differential equation is that, people? Give you a tip. Linear or nonlinear?
Nonlinear is the second word.
No, it's a linear. What would nonlinear be? If you had a coefficient here as a function of y, like sine y times y, then it would be, right? But if you had a coefficient, this is just a linear equation, right? All you got is derivatives added to things. Either you got second order derivative, a single value, and this means this gamma is just a constant. With me, class? Please make sure you know the difference between linear and nonlinear when you go for interviews. Okay, what's the solution? How do you get that? There's two ways you're used to getting it. There's one way of solving differential equations. Usually you saw it in the time domain, not space, but what did you do?
Integrating factor.
you could, actually that's the right way to do it according to this book, but how many know the term Laplace transform? Remember x and t is just a variable. When you do transforms, it allows you to take things, throw them into another domain, then solve algebraic equations, bring them down into the domain you transferred from. In fact, you have the solution. That's the benefit of Laplace transforms. You could use an integrating factor as factor. That's what Wentworth does. Because it's a linear differential equation, I can just say the general solution x will have the form, and here he's going to call it, I guess, some C1e, and it's going to be I think he uses lambda x, and it could be plus C2e to the minus lambda x. And you throw that in there, turn the crank, and you solve it. Do you all remember doing this kind of stuff? So if you do that, we could do the whole thing, but you can take this to the other side. So if you take two derivatives, you find out this. You find that x itself, the functional form x of x, is equal to some constant, and here I'm going to just put it down as some C1, and it can be e to the plus or minus, and here it's going to be j beta x times x. Now, in his book, this, by the way, this equation I'm putting up here is equation 7.36, and then this is one form of the solution. It could also have the form C1, or I'll call it C2 cosine of beta x times x, or it could have the form of the function C3 times sine of beta x times x. I want to just say this. This form would deal with propagation. If things were propagating in the x direction, which they are not, they're confined between 0 and a, then this would be the form we'd go for. If they're confined, it's going to be one of these two forms. Now, because it's the E field in the z direction, now I need to draw that thing up here. And I'm going to do it right here. Draw the drawing, and I'll show you what I mean and why it's true. So I'm going to just go down the cross section of the guide, like so. Here, that's x. Here, that's y. The guide has a width A and a height B. And really it goes this way. And basically, the wave is confined in this direction, but we only have an EZ. You with me? Now, EZ is going in this direction, right? And EZ, if you think about it, you know, assume, actually Z would be out of the board here. Look at this, if it's right-hand coordinate system, right? X cross Y would be Z. But if E only has a Z component, try to appreciate this. Remember that waveguide comes out of the board. It's like solid walls there, a chimney you might say coming out. EZ is the E field. It has to be 0 on that boundary, that boundary, that boundary, that boundary. Do you agree with that? Y'all follow me? Now look at these solutions. It's not propagating, so this one goes away. And it's one of these two. And here's how you always obtain the correct solution. When you look at this, you think, I need the E field to be 0 at x equals 0, right? And it has to be 0 all up and down x equals 0. Do y'all follow me? When you look at the cosine, well, cosine of 0, no matter what beta x is 1, which would mean this C2 is 0, which would give you a trivial solution for x, because that will be multiplying. I erased it. All these x, y, and z are going to be multiplied together to get the E field in the z direction. That's not an allowable solution. The only solution that is possible is this one. So we come over here, and we're going to say that we know, let me do it right here, and I'll try to expand on this. I'm going to say the x form of this is just going to be some constant, doesn't matter what the constant is, and it's going to be the sine of beta x times x. This is a real important part. Now that works at x equals 0, that field is 0. This, remember, is related to EZ. Can everybody follow me on this, class? Where else is it 0? At x equals 0 and x equals a. Y'all with me? So this is how you get beta x. This is real important. So you know the sine, I'll put it right here. The sine of beta x times a, because x would be a, is going to be 0, right? When is sine 0 besides 0? Sine of x equals 0 at x equals 0, at x equal pi, at x equal 2 pi, 3 pi, at x equal m pi. So that means beta x times a is equal to m pi. M is an integer. Do you all agree with that? Or beta x is just equal to m pi over a. Now he has this in his book. You got your book there? Can you give me the equation number for? I'm sure he does. I don't know where it is.
Might have to give me a second.
Hmm?
Might have to give me a second.
You take your time. But this is in his book. That's beta x. Now, think about the y. Remember, we're talking about we got a separation of variables to get EZ, right? Well, the y component, the functional form of y will also have these possible solutions, but only the sign can be possible for a Tm wave. So then we can say y of y will have some, call it C4, it doesn't matter, they're just arbitrary constants, times sine of beta x well, let me do it this way. Sorry. Okay. Let me come back here. This form right here, we got the value for beta x, right? Now we're going to take a look at the y variation, my bad. So now if you take a look at the second derivative of this, I'll put it down one time. Second derivative of y with respect to y squared plus, it would be beta y squared times y. It has to be 0. The solutions will have the form of either exponentials, a cosine, or a sine. You with me, class? The only one that will work is the sine, because the sine of beta y times y is 0 down here. This is where y equals 0, and it has to be 0 over this boundary. If it isn't, it's not a boundary condition that works. So that means from here, put it here. Now I have the second derivative of y. Really, I'm just putting the thing down here. That means y of y has to be some constant, C4, times, and this can be only a sine of beta y times y. But the way we get beta y, because that works on the boundary of y equals 0, that's here. Can you all appreciate that? But it has to be 0 when y is b as well, right? So that means I need the sine of beta y times b equals to 0. And when is sine 0? Any n pi. We're going to use a different integer. Any value of n, integer value times pi. That's the argument of sine. So that means beta y is equal to n pi over b. By the way, these constants n and m are generally acceptable in almost all literature when you see this developed and used. They're just integer values, that's all it means. Usually n, m, and l are only, say, for integers. Other constants like gamma and all that stuff can have any value, really. So now I have that. The last one we need is the z. When we take a look at z, this one I'm going to just take a little time. So for z, we take the second derivative of the functional form of z plus beta z, and I'm calling it beta z squared times z of z, equal to 0. Now, for this one, it's propagating in the z direction, so the sine and cosine won't work. Here, what we do is we say z as a function of z can have the form some constant, and I can just put down, I don't care, C5e, and it will be plus or minus j beta z times z. You can have two terms here. You can have C5e to the plus j beta z times z plus C6e to the minus j beta z plus z. All right? You can, if you want to. But now we're going to get the final form of the solution of EZ for this. Well, I'm at, is there more rain in the forecast for this afternoon or not?
No, at all.
No?
I don't believe. If it does, it'll be like small. It won't be like this morning.
I have something, trying to repair a boat. I have to be outside the door. And I'm tired of getting soaked. So, when we look at EZ, now we know it's equal to some function x of x, some function y of y, and some function z of z, correct? What are our possible functions? Well, that means our EZ will be, now the constants I put in front there don't matter. What we normally do is group all those constants into this. We say it's E naught, and then it's going to be times the sine of and m pi over a times x. Then it's going to be the sine of n pi over times y times b. Then it's going to be e to the plus or minus j beta z times z. It would be in AZ direction. And that is the phasor form of EZ. And I'm going to make a couple of comments here. Please listen here. This is important. When you look at this, one of the obvious questions is, well, we got beta x and we got beta y, didn't we? These are the coefficients of x and y in the sine wave. How come we don't have beta z? Follow me? We're about to get beta z. So what is beta z? Now in Dr. Wentworth's book, please write this down. He does not use beta z. He has beta equal to my beta z. The reason I use beta sub z is it is not the term beta that's generally used for beta. Beta is free space usually. It's omega times square root of mu epsilon. Beta z indicates the wave numbers in the direction of propagation. You all with me? It's how many radians per meter it changes in the direction of propagation, which is the z-axis. So now we're going to go get beta z. And here's how we get it. You remember that?
Quick question, I'm so sorry. The plus or minus in front of the J, is that dependent on direction?
Yeah. If it was propagating in the positive z direction, it would be the minus component. If it was propagating in the minus direction, it would be the plus component. That's all it is, just like propagating waves. As a matter of fact, you can prove this too in a book by Roger Harrington, probably in a lot of books, like Balanis, there's another book, Jackson. What they can do is prove that any waves that are propagating down that thing are the superposition of two plane waves that are actually moving, basically where one plane wave is moving like this. If this is, say this is the electric field in the z direction, yeah, like this. And another electric field like this, you can skip the superposition, set boundary conditions. You can nullify everything but the fields inside it. But I'm not going to, that's graduate level material, but it's interesting to do. Anyway, you come down and get this, right? Now, if we have this, we got to get beta z. And remember the very first equation I had I had the x double prime times yz plus y times, times x times y double prime z plus xy times z double prime plus beta unguided, do you remember that? Equals 0. Now, we go ahead and we take, and we say, well, that means beta x squared, you'll see this in a second, minus beta y squared, minus my beta z squared, plus my beta unguided squared equals 0. Now I'm going to put the values in terms of omega. You with me, class? This is real important here. So now I go ahead and I can say, well, beta z, because that's the one I'm after, beta z squared, is equal to, just follow me. Beta z I'm going to take to the other side. So, is equal to beta unguided, which is omega squared times square root, or omega squared, times mu epsilon. Right? That's this one. I'm taking beta z to the other side. So I got beta unguided is just omega squared mu epsilon. Then I've got minus beta x. Well, what's beta x? It's m pi over a squared. You just were exposed to that, so I don't expect you to remember that. Then I got beta y. Well, that's n pi over b squared. Y'all follow me? I'm just showing you. The goal is getting beta z. That's beta in the direction of propagation. That's the one we want. We don't have it. Now, after that, well, beta z here, if you look at this, that's what we need, is equal to the square root of all this stuff. You agree with that? And in his book, I'm going to try to make sure I show you this. This is equation 7.41 in his book, with one exception. I put for beta unguided squared, I put omega squared times mu epsilon. It's easier to understand that way.
You said 7 point what?
7.41. Do you see it in your book? Back there. Anybody else have a book besides you? What's your first name again?
Holden.
Holden?
Holden, yes, sir.
Wait, is it Holden?
Yes.
Holden. All right. Anybody else have a book? Andrew?
Yeah. What'd you say it was?
7.41. I don't think the new edition changes the number.
Yeah, I see.
Okay? Now, he does not have beta unguided in there. I'm sorry, he doesn't have omega squared times mu epsilon. I would put that in there. Then, I'm trying to find out where he does it right. I want you to understand something. When you have a waveguide, we're going to see why this is true. You know the frequency of operation, right? You know what mu and epsilon are in the guide. You know the dimensions of the guide, A and B. Therefore, if you have the dimensions of the guide, the frequency of operation, which is 2 pi times f, is omega. You know what beta z is. Are you with me? But here's the caveat. Here's one really important thing. Waveguides are high-frequency pass filters. Below any frequency below it, it's called the cutoff frequency, nothing propagates. Everything is attenuated. Y'all with me? So it will not propagate DC. How do you get the cutoff frequency is the next point. And this is real important. You'll see it. I have great faith in this class.
Cutoff frequency.
I think back to when I was sitting where you were going through this stuff. I mean, we had a lot more mathematics, I think, than you get. So we've had higher level mathematics courses and stuff like this. And I remember getting there and I'm thinking, so that's why they use all this crap. I mean, why are we doing separation of variables and all this other stuff? Then you see it applied and it opens your eyes. It just opens mine. Okay, now, when we think about waveguides, there's a critical point. When beta z equals 0, this is real important. When beta z equals 0, it tells you the transitional point where frequencies that allow beta z to be greater, the higher frequencies than what makes beta z equal 0, things will propagate. Frequencies lower than that, they won't. And here's how we find out. I come over here, and I'm going to make beta z 0. With me, class? So I get 0. Maybe I'll do it right here. When beta z equals 0, this is the threshold. I can see that now I have omega squared mu epsilon, right? It's minus m pi over a squared, and then it's going to be minus n pi over b squared. You all follow me, class? This is the point where any frequency higher than that will actually propagate. Any frequency less than that, it won't. And the real reason is, Tom Shumpert was a professor here years ago, he used to say the wave's too fat. If you think about this, this has a sinusoidal variation, right? Well, the lowest order mode we can get here, and you're about to see this, is when this itself is exactly half a wavelength. Any frequency below that will not propagate because it can't meet the boundary conditions no matter what you do. That's the reason. Go ahead.
Well, I was just thinking of something. So the half a wavelength, because that's also half a wavelength's where you get your first top of the peak.
Well, the peak is right.
Wait, no, that'd be when you get your first hump. Your first, like when you draw a sine wave, and you're half a wave.
This is
gonna
180
be-
degrees. That's
Yeah.
exactly half a full wavelength. Half a wavelength. Now, in this direction, we'll have no variation. So the electric field will be in the z direction, but it will only have, if you will, a variation in x like this. So the magnitude will be the same for any given y. All right. But, I mean, the thing is, it will only have this variation. If it was just, we're going to see this, if m was just 1, that would allow that. But you have to have n equal 1 because you have to have a half wavelength this way too. Otherwise, you don't meet that boundary. You with me, class? Just bear with me. So when I take a look at this, I can see, why don't I take omega to the other side and get rid of these negatives, so I have omega squared mu epsilon. We call this the cutoff frequency, so you can put a little c here. And this is going to be equal to this plus this. I just rearranged the equation. Are you with me, class? Please, this is real important. You have to get this. All right, now I'm down here. Now I say that I can take 1 over mu epsilon here, and then I can take m pi over a right here and square it, plus n pi over b and square it. That's equal to my omega c squared. Y'all follow me on this, guys? Well, what is omega c? That's just equal to 2 pi f c, and f c is called the cutoff frequency. Two pi fc squared. Everybody understand what I'm doing? I'm gonna give you an equation number for this one because I want you to make sure you see the reasoning behind this. I hate when he has these things buried up in places, so I'll tell you where this is, but think. What, I tell you, he has this back in equation 7.1, what I'm about to show you, but he doesn't develop it. He just gives it to you. See 7.1, guys? Equation 7.1, he just throws that out. This is where it comes from. Okay, now if you look at this for a second, follow me. I want FC. Can you all see that I can go ahead, let me get rid of that, and I can take the square root of both sides. Everybody agree with that? That's squared, take the square root of both sides. So now I get this. Everybody with me? Now I divide by 2 pi. So I divide this by 2 pi, and that is equal to FC, but I'm not done. You all see this? One thing I'll do, you should do this too. Write FC as a function of m and n. Those are the integer values that are multiplying, or they're inside the sign operations. Sign and now I do this, so I just want you to see this. It's very logical. I have 1 over pi here, right? If I wanted to, I could move that in here. I'd have to square it, right? You see how the pi squares are going to cancel? There's a pi squared there. I move that inside that square root. Now that cancels. So you get this. And that pi goes away. And that is equation 7.1. And these are cutoff frequencies. You must be beyond that cutoff frequency for things to work. The cutoff frequencies for both the TE and TM will have the same form, but there is one big difference. So now, let me erase this and put down some important things you have to consider. Make sure you write this part down. You can get really confused with this stuff if you don't spend sufficient time on it. I mean, really confused. This is probably some of the more confusing things, one of the more confusing topics you're going to come in contact with if you're not careful. So here for TM mode, HZ is assumed 0. That's the definition. This is a rectangular waveguide. Now we have EZ equal to some E naught. That's just a constant. It's going to be times the sine of m pi over a times x times the sine of n pi over, or times y over b. And then we have e to the minus j beta z times the, I'll call it just beta, but remember Whitworth calls it beta times z, and it's in the a z direction. You all with me? It's only one field component. I take a look at this. I know that that beta there, maybe I better call it beta z just to be consistent. That beta z is equal to, please write this down, is equal to the square root of omega squared mu epsilon minus, I'm about to simplify life, m pi over a squared minus n pi over b squared. Now, I just told you that that's the cutoff frequency, right? Can you all follow me? I mean, I've got omega cutoff squared mu epsilon is that. Well, I've got m pi a squared minus n pi over b, that should be a b here, squared right there, which is equal to this, just follow me. I could take that and substitute it in. I could put minus, it could be omega c, omega squared, right here. I hate to waste a lot of time on this, but I'm good at this now. Square in here, it's omega squared, mu epsilon minus, and then it's going to be omega cutoff times mu epsilon. Can you all follow me what I'm doing here? Because this is the definition of omega of the cutoff. Y'all, he doesn't do it in his book, but I'm showing you the proof. Now, if you look at that, a lot of stuff come out in front, doesn't it? Y'all follow me? Here's what you get. When all is said and done, you can pull the omega squared out in front. Or you can take, square root of mu epsilon out in front. I'm sorry. Yeah, square root of mu epsilon out in front. All right. And then you can factor out actually omega. Now listen, when you do that, you're left with, you all follow me? I'm factoring out omega squared mu epsilon. When that comes out in front, it becomes this. Do you all follow me? Because it's squared. But then that becomes 1, and then it's going to be minus, now the mu epsilons cancel, the 2 pi cancels, and then you get minus f c, the cutoff frequency, over f squared. Can you all follow me on that? He doesn't show this part in his book, I don't believe, but I'm trying to show you how the proof comes about. It's important. I'll give you a minute to write it down. With me? Follow me on this one. What this is just beta unguided, isn't it? So what I can say now is, let me write it here. And this is only a cutoff that's beta z 0. Now I can say that beta z, kind of cool, right here that beta z is actually equal to beta unguided. Beta unguided is equal to omega times square root of u epsilon inside the guide. But then it's times the square root of 1 minus fc over f squared. Now, just listen to this. Remember, fc, I said, is the lowest frequency, that it's the threshold where you can't propagate anything below that. Take a look what happens when you're below the cutoff frequency. If fc was less, if you think about this, or sorry, it's f over, wait a second. No, it's this. Suppose now my operating frequency is less than the cutoff frequency, just for a second, all right? If, say, f is 1/2 fc, then this is 2, right? Square it, it would be 4, right? 1 minus 4 is minus 3. The square root of minus 3 is imaginary, isn't it? When you go ahead and take a look at the solution, it's if we get minus or plus j times beta as the actual value for beta z, you see how this is going to actually have a real value, e to the, it would be some real value times the, it attenuates. That's the real truth. It's called an evanescent wave, it'll just decay to 0 very quickly. That's why it's called cutoff. But over here, what we usually do is this. We create something we call k. And k is equal to the square root of 1 minus fc over f squared. And the reason we do it is that way beta z can just be thought of as simply equal to what? Beta unguided times k. Now at cutoff, beta z is 0, and at cutoff, k is 0. Do you all see this when fc is equal to f? This is a real important point. Okay, now back to this. We're still talking about TM waves. Anytime you talk about a TM wave and you talk about the mode it's operating in, usually they'll use the symbol TM and they'll have M, N. TM says the waveguide's in the TM mode. That's the operational mode. That's how the fields are being developed and rendered. But for this, the lowest order mode means the smallest frequency of operation that it could work at require that both M and N are 0. Or I'm sorry, are 1. M and N are 1 in order for propagation. And if you think about that, if M was 0, then this sign of 0 is 0, isn't it? This whole thing would be 0. There would be no sustained field. If N was 0, it would be 0 all the time. M and N have to be 1 or greater, which means the lowest order frequency that can actually propagate. And this is the lowest order or the smallest frequency, the least frequency, lowest order frequency for TM is TM11 is the mode, and that means that cutoff frequency for 11 would be equal to 1 over 2 square root of mu epsilon. And here it would be 1 over a squared plus 1 over b squared. Y'all follow me? That's for T. And we're going to see for TE, for transverse electric, you'll have cosines instead of sines defining, and the lowest order mode will be the 1 ohm mode. And that is the cutoff, that's the lowest frequency that can propagate, period. You all with me, class? Okay. One on this topic, if this is beta in the z direction, right? And he uses beta here. Well, while I'm on it, what's the wavelength of you? Let me put it over here. I know I'm throwing a lot at you, and you'll get plenty of example problems, and we'll do some, but so if you think about this, let's get phase velocity. What's phase velocity in the general sense?
Omega over beta.
Right. It would be omega over beta if it was unguided, right? This is a guided wave. So it's not beta. The direction of propagation is beta z. And this is only the phase velocity. So it's equal to omega, and what is beta z? Well, it's equal to beta, right? Unguided.
Okay.
And it's times what?
Okay.
Yeah. All right. Good times. No, actually, let's do it times k. You're absolutely right. That's the easy way, right? And what's k? Well, it was here a second ago, but it's gone, right?
So
K is equal to square root of 1 minus what?
cut off.
FC over F squared, right? Remember, you got to get these in the right order. FC's on top. It's less than F because F has to be greater than that for propagation. All right, now what do you notice about this? Well, now I got one. Let me do it. V phase here, omega over beta unguided. Omega, what is beta unguided? Omega times square root of mu epsilon, isn't it? Right? Times K. Omegas cancel. So I have 1 over the square root of mu epsilon divided by K. Do you agree with this, everyone? My handwriting is starting to slip. Are you all with me? Well, what is 1 over the square root of mu epsilon? If it was mu naught epsilon naught, it would be the speed of light. Agree? But it is the velocity that the wave is propagating with in free space, if there was nothing confining it. You know, so this is really, a lot of times they do it like this. They say, well, the phase velocity, which is not the velocity of energy, is really equal to c over the square root of epsilon relative. Now, the reason they do that is you don't have magnetic materials in waveguides almost ever. So they assume mu relative is 1, and then it's going to be divided by k. And that would be the phase velocity. You'll notice, if you take a look at that, k itself, as the frequency goes to infinity, becomes 1. So as the frequency goes to infinity, basically, you don't have a wave ricocheting, you have a plane wave. That makes sense, because if the frequency goes to infinity, this is trillions of wavelengths across, and it looks like just planar propagation. So that's phase velocity. What's wavelength in the guide? Well, what is wavelength generally? It's what? 2 pi over beta, so over beta z. So there's beta z, beta unguided times k. And now you can see what? Oh, you can just write it down. It's going to be
Is this, you said wavelength in the Y?
in the z direction.
Wavelength in, what's the
Got it.
subscript on the Y?
Here,
On the lambda.
lambda of the guide. So, lambda of GUIDE. And what that means is if I was looking at this thing and this direction, we're finding the wavelength down here. Now the wavelength in the guide goes to infinity at cutoff. The wave literally bounces top plate, bottom plate, top plate, bottom plate. Nothing propagates. So if you look at this, that's 2 pi beta unguided omega square root of mu epsilon here. and then times k. Well, k goes to 0, this goes to infinity at cutoff. Last thing I want to say before I get out of here. Remember, this is phase velocity. It is not the velocity of energy propagation. I want to make this last point real clear. You all agree with that? That's phase velocity, and I'll write it down. The velocity that energy propagates, or it's called the group velocity, is equal to k. Now k's on top, so this goes to 0 at cutoff. It's going to be k, and it's going to be divided by the square root of mu epsilon. And here it becomes k, and it's going to be times c over the square root of epsilon relative. Now remember, k, the largest value k can have is 1. And as you get closer and closer to cutoff frequencies for lower and lower frequencies, it goes to 0. So energy, the actual rate that energy propagates will go to 0 at cutoff. Y'all with me on this? I don't know if in physics you had anything like this, but the last thing, I guess I got one more minute to talk about is what do I mean by phase velocity? So I try to explain it this way. Phase velocity has nothing to do with real photons or energy moving. Phase velocity has to do with a mathematical point that we construct that is really an intersection, that the locality intersection point is moving, but nothing is really moving. Here's what I mean by that. Think about, just for a second, if you have a shoreline here. Assume this is a shore. And suppose I have a wave moving in this direction. This would be like the phase front. And you got a surfer on this wave that it's moving in, right? Take that and move it this way. Now take that phase front and assume it's moving along this direction. This is a constant phase front. You can put a surfboard here if you want. So if this wave is moving along that shoreline, right? There's no wave breaking on the shoreline. It's moving parallel to it. You all see that? This velocity here is the phase velocity. That's the phase velocity. Now, if I take this wave and I do it, and I have, here's the front, the high point, and here's my surfboard here, but this wave is moving in that direction. Are you all with me? Well, there's an intersecting point where this phase front breaks on the shore. That is moving at the actual phase velocity. I should say this is the true velocity of the wave. It's moving like this. But this point is moving faster. Take a look at this. As this gets sharper and sharper, you'll see this, I guarantee you. Suppose I have something like this. Here's my phase front. And now I'm going to only move a small distance here. Look at how much of a distance I move here. You all see that? That distance move between here and here, assume a certain amount of time happened. This is moving at the velocity of the wave in free space, you might say. Here, it appears that it moved from here to here because that's where the phase point moved from. That's the phase velocity. It's a mathematically defined point that's moving. There's nothing really moving that fast, if you want to think of it that way. You all with me, class? So just keep that in mind. Phase velocity can get you in real trouble with wavelengths. Okay, I'm going to give you some homework now. Here's a giveaway. For the TE mode, we did TM. Instead of sines, you'll have cosines. And the lowest mode that can propagate will be a 1-0 mode. I'll do that on Friday. So a logical question is for your quiz, what will the quiz be on, correct? I'm going to ask you something about waveguides because with oblique, if I give you an oblique incidence problem, this is my concern. Those things tend to cause you guys to go bananas with the equations when I get the 8 to 1, because it could be TE or TM and Brewster, and it can get really time consuming. I'll give that on an exam, but here it could be a little tricky on Friday. So I'm going to give you something regarding to what we covered today, okay? I'll give you some homework and I'll go over it. See you Friday. Oh, did you all understand? I think my best is trying to make it as abstract as it usually is.